Stanford University.
This is Sanjay.
Thank you.
Did we get Sanjay on the recorded? Yes? Okay.
So we just want to announce that we're trying to collect up all the old lectures, the video lectures that are on YouTube, in one kind of a collection. And the idea is for everybody who's taking classes online and offline, we can actually have an easy way to navigate through all the lectures instead of have to hunt for them, right? So we're passing out a little sheet that's got a web address on it. Right now, this is the temporary housing for it, and it should be good until whenever. But when we do get a final home, we'll have a link that'll directly go to it as well. So this link should be good for hopefully all eternity until we hit Horizon and all that good stuff.
Right. Okay, so this is the address. Let's see, http://new packet tech, one word, newpackettech.com/resources/Susskind. That's the address where it's sort of the website for the class, or will be the website for the class. And it's for anybody outside, inside, where they can easily access, without all the confusion that's taken place up till now, easily access all of the lectures that are online. All right. We have been discussing a simple quantum field, and we're not finished with it. I have to take a 2-year course, and believe me, a real course in quantum field theory is genuinely 2 years of work. It really cannot be done in 1 year sensibly. I have to take that 2 years of quantum field theory and condense it down to a couple of lectures. We've already taken a couple of lectures, but I think we've had some forward motion. I want to take the very, very simple version of a quantum field that we've already discussed. Well, first of all, remind you what it is, and discuss how it is used, again, to describe particle processes. We've done a bit of this. We've talked a bit about how the quantum field can code or codify scattering processes or creation and annihilation processes of particles. But I want to go into it in just a little more depth so that you can see where some of the really interesting aspects of quantum field theory come from and how they influence questions like energy conservation, momentum conservation. How do those things, how are they related to these quantum fields that we've discussed? Okay, before I do so, we need a little bit of mathematics, a little bit of formal mathematics, not much. It's mathematics that we've done before in these series of classes, but I want to get them up on the blackboard. The first thing is the Dirac delta function. All right, the Dirac delta function, just to remind you what it is a function which is the sort of a limit of a genuine real function. It's a function of, let's say, its coordinate. Let's for the moment just call this coordinate anything. It could be x, it could be k. Let's just call it y so that we don't prejudice whether it's something that I've called, that I've defined previously. The Dirac delta function is a function which is a sort of lump. It's concentrated someplace. It's concentrated someplace and not other places. But it's the limit of an infinitely sharply concentrated function. So we imagine that we can go to a limit where this lump-like function is infinitely narrow. Now, I can't draw it as infinitely narrow, so I'll draw it with finite width. But imagine in your mind narrowing it, narrowing and narrowing it. Now, of course, if you narrow it without raising its height, the area under it will decrease and decrease and decrease to the point where there's no area left under it. So what I want to do is to keep the area under this function fixed as I decrease the width. So as I decrease the width, I'm going to raise up the height of it in such a way that the product of height times width stays constant. How constant? 1. just 1. An area of 1 located someplace infinitely narrow, that's called a Dirac delta function. If this point is y equals, let's call it a, just to locate the particular point, then the Dirac delta function is delta of y minus a. And delta of y minus a is 0 whenever y does not equal a, over here or over here, and equals something infinitely sharply peaked at y equals a. That's the Dirac delta function. And it has the property, by definition, that the area under it, the integral with respect to y, is 1. So it's so narrow and so high that the area is 1, and it's concentrated at the point where the argument of the function is equal to 0. In other words, when y equals a. That's the Dirac delta function. Okay, now I want to show you how the Dirac delta function emerges from a certain integral. An integral that we will come on many, many times. Let's take the function e to the I kx, e to the I k x. Now, again, as we discussed last time, we're discussing this on an interval, which is a periodic interval, which has total length all around it equal to L. So the distance around here is equal to L. I don't know if this, just the distance around it is equal to L. It's periodic. And so functions that live on this periodic space here should be periodic, meaning to say they should come back to themselves after one full loop. Okay. Now, what is k? First of all, k is one of the allowed values of wave number on this, in other words, one of the values of k where e to the I kx is periodic. So let's assume an allowed value there. And let's take this function and integrate it over the entire cyclic x dimension here. We could take x going from 0 to L, or for symmetry, I could take it to go from minus L over 2 to L over 2. In other words, instead of starting x at 0 and going to L, I could start it at minus L over 2 and go to L over 2, put 0 at the center here. Nothing special about this. It just symmetrizes things nicely so that the negative half and the positive half are symmetric. When you leave the space, if you're marching along and you come to L over 2, you pop back up at minus L over 2. Okay. So we're taking a function, a periodic function, e to the I kx, and integrating it from minus L over 2 to L over 2. What is the answer? Okay, first of all, what is the answer if k is equal to 0? L. This is L, let's write is equal to L if k is equal to 0. And what if k is not equal to 0? 0. Because if you take a periodic function that oscillates and you integrate it, then you get 0 because it's positive as much as it's negative. Only for k equals 0, in that case, of course, this doesn't oscillate, it's just equal to 1, then you get L. Okay. So, now let's think of this as a function of k. Let's draw the k-axis. Let's draw the k-axis. Here's the k-axis. Now, k is not just any number. It's one of the allowed numbers. So it's discrete. Does anybody remember what the allowable values of k are? Two pi n over L, right? In particular, as L gets bigger and bigger, the distance between neighboring values of k gets smaller and smaller. And eventually, as L gets infinitely big, these discrete intervals shrink to 0. Okay, so now what's the distance? Let's put k equals 0. K can be positive or negative, incidentally. Let's put k equals 0 right over here. Here's k equals 0. All right, what's the interval between neighboring values of k? 2 pi over L. That's the distance from k equals 0, or from n equals 0 to n equals 1, for example. 2 pi over L. Now, let's take this function. This function is a function of k, of course. I've integrated it over x. It's only a function of k. What is it equal to? Let's plot it on here. It's equal to L when k is equal to 0. So right at k equals 0 here, it's high and it's equal to L. Let's just give it a slight width just for the purpose of drawing it. Just for the purpose of drawing it, right at k equals 0 here, it has a height equal to L. But at k not equal to 0, it's 0. That's what we concluded. At k, it's equal to L if k is equal to 0, and it's equal to 0 if k is not equal to 0. So, how high is it? It's height L. How wide is it? Well, one interval. You can't think of anything smaller than one interval on here. It has a width 2 pi over L. What's the area? If I imagine giving it that much of a width, what is the area under it? 2 pi. So that means that this function is 2 pi times the delta function. This function here is 2 pi times delta of k. Why delta of k? At k equals 0, it's not equal to 0. At k equal anything else, it is equal to 0. Now, what is the meaning of this? The meaning of this is in the limit of very, very large L. This becomes a very, very narrow, very, very high function whose area is equal to 2 pi. Okay. We'll keep that in mind as we go along. This is called the Dirac delta function. And we can now say, let's now go to the limit of very large L. If we go to the limit of very large L, in other words, we're making these intervals progressively smaller and smaller, we're really approaching the situation that really does define the Dirac delta function, then this integral goes all the ways from minus infinity to plus infinity. So just think of this as a formal prescription for an integral of e to the I kx, and the rule is it gives delta of k, 2 pi times delta of k. This is equal to 2 pi times delta of k. That's something of importance, that when you integrate over a function of e to the I kx like this, dx, you get a Dirac delta function of k. Let's see if you can guess. Supposing instead of doing the integration over x, I did an integral over k, exactly the same integral, except it's not at all the same integral, e to the I kx. But instead of integrating dx, I integrate dk. What must that be? It's a function of x. But it's exactly the same structure here, except I just interchanged x and k, right? X and k appear symmetrically here. So if I interchange x and k, this doesn't change. But I've changed the integral over x to an integral over k. So this is now some function of x, but what is the function? 2 pi times delta of x. So these are two little observations that we will see happening. We'll see their utility occurring in a number of places. All right, that's the Dirac delta function. That's our first little bit of mathematics tonight. The hell was that? Next little bit of mathematics. I taught you what a ket is. A ket is a symbolic notation for a quantum state. I also think I told you.
You didn't use the word ket.
I didn't. What did I use? I did. And I told you it was half of a bracket.
Oh, yeah, that's right.
Yeah. Okay. It's the other half of the bracket now that we want to talk about, the bra, otherwise known as bra. These are just notational devices. For our purposes, these are simply notational devices. And the question is, when do you use the bra and when do you use the ket? For our purposes, we will think of kets as initial states in a process. If a process starting with some initial state is described by some quantum state, we'll describe the initial state as a ket vector. Initial. In. Final states we will describe by bra vectors. And when you put a bra vector next to a ket vector, you make a bracket. This is simply a bunch of symbolic manipulation, but at the end, what comes out of the symbolic manipulations are numbers. Okay, numbers, experimental numbers. So I'm going to teach you now some symbolic manipulations. For every, let's go back to the harmonic oscillator. For the harmonic oscillator, we characterized the quantum states of the harmonic oscillator by occupation numbers, n. The number of excitations of the harmonic oscillator, the number of times, the number of units of energy that's been put into the harmonic oscillator. We can also describe it, that's a ket vector. That's the ket description of a particular quantum state. We could also write it in terms of a bra vector. So far I haven't told you anything. I've just told you there's two ways to write the same thing. You say, what's the difference between them? Not much. Okay? But if we are clever in our use of this notation, it will help us do some bookkeeping that's interesting. All right, now, first of all, there's the notion of the inner product between a bra vector and a ket vector. Now, all of this is in our past quantum mechanics classes, and I refer you back to it. We're going to go through it lightning-like tonight. If I have a ket vector n and a bra vector m, I can put them next to each other, and putting a ket vector next to a bra vector in this way always gives a number. The ket vectors are abstract things, the bra vectors are abstract things, but the product of two of them back to back, or I don't know, front to front, I'm not sure which, in that form is a number. This number, now m stands for some quantum state, the nth quantum state of the oscillator, and n stands for the nth state of the oscillator. This number, this is definition now, is equal to 0 if m is not equal to n, and it's equal to 1 if m equals n. So the bra vector and the ket vector, for the same value of n, have a product which is 1. It's called the inner product between these two. It's 1 if n equals m. It's 0 if n is not equal to m. Or to write it in a unified form, we can write it as delta nm, whose definition is it's 0 unless n equals m, and 1 if n is not equal to m. It's kind of like the Dirac delta function. It's a discrete form of the Dirac delta function. All right, this is notational. This is just notational tricks for things. Now, let's come to creation and annihilation operators. What I want to get at before we go further is how creation and annihilation operators act on bra vectors. I've told you how they act on ket vectors, and I have not told you how they act on bra vectors. Now, of course, you can say, of course, I haven't told you, in fact, I haven't even told you the rules which would allow you to deduce how they act. But I'm going to show you how they act and then show you why this rule was particularly nice. All right, so let's take creation operators first of all. What does a creation operator do when it acts on the nth quantum state of an oscillator? It multiplies it by square root of n plus 1 times the n plus first state. What about the annihilation? The annihilation gives you square root of n times n minus 1. So one of them raises the quantum state, one of them lowers the quantum state, and in each case they multiply by the appropriate square root of n. Now we can ask, now we're asking for a definition. This is not a theorem which we want to prove. This is a definition of how creation and annihilation operators operate when they act on bra vectors. So how shall we take A plus to act on the nth bra vector? And I'm going to tell you now what the rule is. The rule is that however it acts on the nth vector, it gives another vector, another bra vector, of course. Let's circle that bra vector. And now take its inner product with the mth ket vector. However this acts, whatever it gives another bra vector. That's the rule. When an operator acts on a ket vector, it gives a ket vector. When it acts on a bra vector, it gives a bra vector. And the notation is such that when an operator acts on a bra vector, you put the operator to the right and hit it to the left. When it acts on a ket vector, so it's a neat notation. The rule is that you get exactly the same answer as if you did what?
Times you apply A plus M.
Allow A plus to act on M and then take the inner product with N. See, there's two distinct operations. However A plus should act on N, we'd like to find out how it should act on N, we're going to define it so that you get the same answer for this bracket as if you allowed A plus to act on M. Well, I've given you the rule for how A plus acts on M, and then take the inner product with N. Okay. So let's see if we can figure out from this set of abstract principles or abstract definitions, how A plus acts on N. All right, let's see. Let's first take the bottom line here, the bottom line. Let's calculate it. It's N. And now A plus acts on M. What does that give? Square root of m plus 1. That's a number. We take it outside. Square root of m plus 1. And then what? M plus 1. What does this give? This factor gives 0 unless n is equal to m plus 1. All right? If n is the same as m plus 1, then you get the number square root of m plus 1, which also happens to be the square root of n, of course. So that's one way of calculating that's this over here. But notice, it only gives an answer, a non-zero answer, if this is 1 unit higher than this. Sorry. Yeah. Sorry. It only gives an answer if m is 1 unit lower than n. If m is 1 unit lower than m, then A plus comes along, increases m by 1 unit, and then we get a non-zero answer. So the only way to get a non-zero answer is if m is 1 unit lower than n. Well, let's look at this over here. Supposing that A plus acted on n to raise n, then we would only get an answer if m was 1 unit bigger than n. But according to this rule, we only get a non-zero answer if n is 1. I think, all right, let me say it accurately. I get my, okay. From this form, we see that n has to be 1 unit bigger than m to get a non-zero answer. N must be 1 unit bigger than m. All right? If, on the other hand, A plus increased the value of n over here, then we would only get a non-zero answer in the opposite situation, where n was 1 unit what? Less than m. Right? So this can't be the right rule that when a plus acts to the left, that it increases the index here. What it must do is decrease the index here. And in fact, that's the definition. That's the correct definition. When a plus acts on a bra vector n, it doesn't increase n, it decreases n minus 1. And what about the numerical factor there? The correct numerical factor is just square root of n, if you want to. You can work this out. All right, what about na minus? What does that do? Well, the answer is, I've given you enough rules that you can determine yourself what it does. What it does is it increases n plus 1 times square root of n plus 1. In other words, to make the story short, when a plus acts on ket vectors, it increases n and multiplies by square root of n plus 1. A minus decreases n and multiplies by square root of n. When a plus and a minus act on the bra vectors, they just interchange. A plus decreases n and multiplies by square root of n. A minus increases n and multiplies by square root of n plus 1. That's the rule. That's the rule which leads to a very lovely calculus that's useful in quantum mechanics. So calculus meaning now tricks for computing simple things. Let me give you an example. Let's calculate in two distinct ways the following quantity. Let's take a plus a minus. Remember what that was? What did that stand for? Yes, it stands for, it's a quantum mechanical operator that stands for the occupation number, the number of quanta in the state. And let's calculate this quantity here. A minus, I'm sorry. A minus. Let's calculate it in two different ways. Now, for those who've studied some quantum mechanics, you'll know that this expression stands for the average value of whatever this quantity is in the quantum state n. But for the moment, let's just calculate it as an abstract exercise. But let's calculate it two ways. In the first way, let's allow this operator to act to the right. First, a minus acts to the right. What does a minus give when it acts on this? It gives square root of n times n minus 1. We still have a plus, which we haven't used up yet, n. Now, numbers come on the outside. Numbers like square root of n, they come on the outside, square root of n. Now, what does a plus do when it acts on n minus 1? It pushes it back up and multiplies by what? One integer higher than what appears here, so that means again square root of n. That gives us 2 square roots of n, which means n, times n what? N. A plus on n minus 1 brings us back to n, and nn, what is that? That's just 1. So it just gives us n. If it acts a plus a minus when sandwiched within the quantum state n, just gives us the numerical number n. What would happen if we did it in the opposite, not in the opposite order, but by acting to the left on the bra vector? Let's do it. What happens when a plus acts on n to the left? It gives us n minus 1 times the square root of n. But we still have to act with a minus. What does a minus do when it acts on n minus 1? It raises you back up. Raises you back up to n and gives you another square root of n. So you see, with this definition, that the creation and annihilation, or the raising and lowering, get interchanged when you go to their action on bra vectors and ket vectors, then it doesn't matter which way you imagine these operators operate, we'll get the same answer. That's a useful notation. And so when you see a thing like this, you don't have to ask, should you operate with this to the right and then take the inner product with the left-hand side, or should you operate to the left and then take the inner product with the right-hand side? You get the same answer. That's the beauty of that particular definition here. All right, that's good. Now, what are we going to do with all of this? Well, of course, we're going to study quantum fields, which are objects built out of these creation and annihilation operators. Let's go right there. Let's go to the quantum fields. Go back to a simple quantum field that we've discussed already. And then come to the description of quantum processes, scattering processes, creation of processes, annihilation processes, and so forth, how they're described by quantum fields, or how they're described in terms of mathematical expressions involving the quantum fields. Why are we interested in processes like collisions and creation and annihilation processes involving particles? Because in the microscopic world, that's about all we can do. If we want to do experiments, the only real handles we have on experiments is colliding particles together and see what comes out, and describing those processes, how the initial state of the particle, of two particles, for example, morphs into some other state involving 5, 7, 9 particles, 4 particles, whatever it is. The tool for that is quantum field theory, and we're setting up some simple examples. All right, so let's go back to the definition of the simplest quantum field. The simplest quantum field, we took it to be a function of only one coordinate, namely x. There's no reason why we can't think of x, y, and z here and make position into a three-dimensional thing. If we do so, momentum also has to be, incidentally, we'll work in units in which h bar is equal to 1. I don't think tonight the speed of light will come into anything. But what's the connection between momentum and k if h bar is equal to 1? They're the same. Normally, you would have an h bar over here, h bar k. But if h bar is set equal to 1, k and momentum are the same thing. Okay? Right. Okay, so we concocted a thing which we call a quantum field associated with the point of space, x. As I said, x could be a three-dimensional point of space. If it is, then k has to be three-dimensional. If we're living in 3 dimensions, then the momentum is three-dimensional, meaning to say it has 3 components, and then k will also have 3 components. But other than that, the formulas I'm going to write down are pretty much the same in 3 dimensions, whatever number of dimensions we're doing. Psi of x was a sum over all the allowed values of momentum. If we're talking about the universe on a circle or the periodic universe, then these are the k's, which are 2 pi over L times an integer. If we're talking about an infinitely big universe, then k can be anything, any number. Sum over k, summation over k of the creation operator for a particle of momentum k times e to the minus I kx. That now has become a quantum field. There's a conjugate quantum field, and now we pretty much, if we're quantum mechanics people, we talk about the Hermitian conjugate. If we're classically oriented people, we simply talk about the complex conjugate. We can call it psi star or psi dagger of x, the complex conjugate, which is a similar thing involving annihilation operators times e to the plus I kx.
Excuse me?
Yeah.
Is this a definition or
This is definition. This is definition. But, you know, definitions, the question, it's always appropriate when somebody gives you a definition to say, why is that the definition? Right? And then the usual answer is wait. Wait till you see how we use it, and you'll see that it's a useful definition. Okay? So I'm afraid that's the situation here. Why is this the definition? Because this is a useful definition. I could have put something else here, and it would have been a useless definition. So it's premature to ask why this is the definition, but it is a nice, simple expression. It's not very complicated. Sum over the allowable values of momentum, creation operator times e to the minus I kx, or the complex conjugate, which has annihilation operator times e to the plus I kx. Now, I'm going to do something even a little bit fancier. Okay? I'm going to give these psi of x's some time dependence. So far, they don't depend on time. The definition does not involve time. But I'm going to introduce some time into the game. And how do I introduce time? Why do I introduce time? Well, remember that there's a connection between the momentum, the wave vector k, and the frequency of an oscillation. These are fields. These are fields. Fields oscillate. As it's written now, it doesn't oscillate. It doesn't have any time dependence. If this has anything to do with a real field, waves, and so forth, we better introduce some time into it. Well, that's not so hard, because we remember that for each value of k, there is a frequency. Frequency tells us how things change with time. Supposing I have an object, a mathematical object, which has a certain frequency, omega. How do I write the function that oscillates with frequency omega? E to the I omega t. E to the I omega t, which also happens, of course, to be cosine omega t plus I sine omega t. This is a function with a definite frequency. The frequency is omega. All right, now, in past lectures, I pointed out to you that for various kinds of waves, each k is the wave vector. It's inversely related to the wavelength. For each k, there is a frequency. So we can say that there is, for each k, there is an omega of k. And each oscillation, each time we see an e to the minus I kx, we can put in front of it an oscillation, not in front of it or behind it, an e to the I omega of k times t. Now, this thing has not only space dependence, but it has time dependence. And moreover, it's time dependent. We do the same thing here, of course, e to the minus I omega of k t. Let's erase psi dagger for the moment. We'll come back to it. I want more room on the blackboard. Here's an object which has both space dependence and time dependence. The time dependence has been arranged in such a way that for each value of the wavelength, or k, it oscillates with a time dependence which is just the right time dependence for that wavelength. Okay. This is now a function of space and time. It truly is a quantum field now. It varies in space and time. Okay, I want to take an example and show you that in the example, there is an equation, a wave equation for psi of x and t, and see if we can figure out what the wave equation is. See if we can find the wave equation for psi of x and t, knowing the connection between omega and k. Now, I haven't told you what the connection between omega and k is. All right? But let's suppose that we're talking about a non-relativistic particle. In other words, I'm not talking about a photon. I'm talking about a species of particle which moves with much less than the speed of light. We're working in the approximation in which everything is non-relativistic. Okay, when h bar is equal to 1, let's put it over here, h bar equals 1, omega has another name. What's the other name for omega? Energy. Remember, energy of a photon or energy of a quantum, of a single quantum. We're talking about a single quantum now. The energy is h bar omega. If h bar is equal to 1, omega and energy are the same. Momentum is equal to h bar times k. So when h bar is equal to 1, energy is frequency and momentum is wave number. Okay. What's the connection for a slowly moving particle? Slowly means only slowly moving compared to the speed of light. What's the connection between energy and momentum? Right. Energy of a slowly moving particle is the square of the momentum divided by twice the mass. This is, of course, the same thing as writing energy is equal to 1/2 mv squared, and P is equal to mv. All right? If we solve for V and plug it in into here, we get this relationship here. Okay, that also tells us now the relation between omega and k. K squared over 2m. Right? So now we really do know the precise form of psi of x and t. It's a sum over the allowed values of momentum, and omega of k is not just some arbitrary omega of k, but it is k squared over 2m. With that proviso, psi of x and t solves or satisfies a differential equation, a wave equation. Let's see if we can see what the wave equation is. First of all, in wave equations, derivatives with respect to space and time enter and are equal to each other in some form. That's what a wave equation is. Equations for how space variation is related, or how time variation is related to space variation. So let's consider first the time derivative of psi. What's the time derivative of psi? I'm going to call it psi dot, standard notation for time derivative. Psi dot we obtain by just differentiating the time dependence with respect to t. That's equal to sum on k, a plus of k, e to the minus I kx, times what? Times I omega inside the summation, I omega of k, e to the I omega of k t. All I've done is say every time, this is still under the summation here, every time I differentiate with respect to t, it pulls down a factor of I omega. All right, so that's psi dot. Now let's look at the space derivatives. What is the space derivative? dψ by dx. Well, we do exactly the same thing. Every time we differentiate with respect to x, it pulls down a factor of minus ik. Okay? So this is equal to the same kind of thing, summation of minus ik a plus of k times e to the minus I kx, e to the I omega of k t. So differentiating with respect to x always just pulls down a factor of ik. Differentiating with respect to time pulls down a factor of I omega. All right. Now, there's no simple relationship between this and this. Why not? Because omega is related to k squared. If omega was simply related to k, for example, if omega had to be equal to k, then we would just say psi dot is equal to d psi dx. For example, imagine a world or a kind of particle where the frequency is in fact equal to k. That's a very simple situation. In that situation, I omega k is the same as apart from a minus sign, is the same as ik, and we would just say that such a field satisfies a equation that psi dot is equal, I think, to minus d psi by dx. Is that clear? Yes. All right. But that's not the case here. We have to have omega equals k squared. So how can we get k squared? Take another derivative. Each time we differentiate, it brings down a factor of ik. So let's differentiate again. That brings us minus ik squared. What's minus ik squared? I think that's minus k squared, right? Minus k squared. Minus, with a minus sign. But now, k squared is 2m times omega. K squared is 2m times omega. So let's write that, 2m times omega. And let's divide the left-hand side by 2m. 2m is just a number.
Excuse me.
Yeah.
I'm confused. Is the minus sign really supposed to be there? I thought you had minus I.
Let's see. Let's check. When I differentiated with respect to time, it gave an I omega. So that's all I omega. Now, when I differentiated with respect to k, it gave a minus ik, and I did it twice. So that gives minus ik squared. What is minus ik squared? Minus k squared. This is minus k squared. So yes, as far as I can tell, the minus sign is there. Okay. There was a minus k squared, and then I substituted for minus k squared minus 2m omega. And that's where this came from. Okay, I'm more familiar with this in the form in which we divide both sides by 2m. This doesn't matter, of course. Let's divide it by 2m, and we get 1 over 2m times the second derivative of psi with respect to space squared is omega times all this stuff, but that's clearly proportional to psi dot. What's the relationship?
You got an I omega there.
Here we have an, yeah, we better, yeah. There's going to be an I in the formula. We can divide by I, which is the same as multiplying by minus I. Okay, to make a long story short, the right equation should be minus I psi dot, that's the time derivative of psi, divided, or is equal to 1 over 2m times the second derivative of psi with respect to x squared. Now, do I have the sign right or not? Of course I don't. I never get it right. Okay. Now is it right?
No, you had it right.
I'm not sure. 1 over 2m, not 1 over 2m squared. 1 over 2m. 1 over 2m. Okay. Let's see. Is the minus sign there or not? Let's put a minus here, and then there's a plus here. So It looks like this. It looks like it's the plus sign. As far as I can tell, it's the plus sign. Yeah.
Well, it's just that you have the I on the opposite side of the equation than I do, so.
Well, of course, that will do the trick, right? Okay. Does anybody know the name of that equation? It's the Schrodinger equation, right? But it's not the Schrodinger equation for the same thing as in elementary quantum mechanics. In elementary quantum mechanics, psi is just a function of position. It's not an operator. It doesn't do things. It's just a thing whose square is a probability. Here, it is an operator. When it acts on states, it creates particles. It annihilates particles. This is an instance of the relationship between particles and quantum fields. Quantum fields are operators. They happen to have the same equations as the Schrodinger equation of elementary quantum mechanics. They are very closely related, but they're quantum mechanical operators. They're observables. You can observe them. Under what circumstances do they behave like classical fields? In other words, that you can measure them, and the same way you measure the electromagnetic field. The answer is that they behave like classical fields when the number of quanta is very large. When the number of quanta is large, then the magnitudes of the fields are large, and the quantum fluctuations are small, the quantum uncertainties are small, exactly like a harmonic oscillator. A harmonic oscillator, if it's got a big motion, behaves classically. If it's only got one quantum unit of excitation, it behaves very quantum mechanically. So this is an example, as I said, of a quantum field, and it has creation and annihilation operators in it. Nevertheless, it's a thing which satisfies an equation, and the equation is the Schrodinger equation. This is obviously a more advanced notion of the Schrodinger wave function than just saying it's a thing whose square is the probability for a given particle. It's something a little bit different. Okay, and as I said, it is a quantum field. It's the simplest version of a quantum field. How do we use it? How do we use it to describe processes? Okay, so I'm going to give you and we've already talked about this a little bit. What I didn't talk about, and which I want to come to now, is energy and momentum conservation, and how energy and momentum conservation are codified or codified, whatever the right word is, in the various dependencies of psi and the way that we describe various processes. I want to imagine now describing the very, very simplest process in which a particle scatters off a target. The target in this case is a thing which is so heavy that it doesn't recoil. The particle comes and either reflects off it or scatters off it. In 3 dimensions, it could have its trajectory changed. In other words, it could be coming in from the left and go off straight ahead. But what can you say about a particle scattering off an ordinary target, a target that's just stuck there, it doesn't move, stays there forever and ever? Which of the conservation laws would you expect to be true for that particle? How about momentum? Just a moment. I've got to.
Yes, of course. We've got refraction, reflection, and
What's that?
reflection, refraction, and absorption.
Well, let's forget absorption for the moment. All right? The particle comes in and goes out, so it's not absorbed. But yes, it could be reflected, bing bang. It could be refracted, in which case its direction of motion is changed. In any case, the momentum of that particle generally is not the same coming in as going out. Of course, secretly what happens is momentum is really conserved, but what happens is, of course, the target absorbs some of the momentum. But let's just fix the target. Let's imagine nailing down the target, and the target is not part of our mathematical description, or the motion of the target is not part of our mathematical description. Then in the mathematical description of a particle scattering off a target, the momentum of the particle is not conserved. All right. What about the energy? Yeah, the energy of the particle is conserved. If you take a tennis ball, well, a tennis ball is a bad example because it, it heats up when you throw it against the wall. But an idealized tennis ball where you can ignore heat, you throw it against the wall and it bounces off. What can you say about the way that it bounces off? You can't say that momentum is conserved. The momentum has gone from that direction to that direction, but the energy is conserved. So how can we see that in some simple model of the scattering process, that momentum is not conserved and energy is conserved using these wave fields? So we talked about this last time a little bit, and I showed you how you could describe a process of scattering, creation, annihilation, and so forth using these quantum fields. So here is a model. Here is a space is horizontal, time is vertical, and the axis over here represents a target. It's fixed in space. It neither, and it goes on and on forever into the past. It just sits there. And a particle comes in. It hits the target at some point and either bounces off or goes forward or scatters into some other direction. So we describe the initial state by saying there's one particle with a momentum k. Let's call it k in for initial or incoming. And then a particle goes off, having scattered off the target. And let's use a language now. It's absorbed by the target and suddenly re-emitted by the target. Okay? Think of it, instead of just thinking of it as bouncing off the target, let's in the back of our mind have a picture in which it is absorbed or annihilated by the target and then instantaneously recreated by the target, but possibly with a different momentum. Let's call that final momentum K final. Let's just call it Ki and Kf. Initial and final. And what are we interested in? We're interested in the probability amplitude, the quantum mechanical probability amplitude that the particle scatters from momentum K initial to K final. Now, one more ingredient. I'm going to assume that the scattering can happen with equal strength, equal at any time, always at the same place. We're going to place the target at x equals 0, but we're going to assume that the scattering process can occur at any time. Whatever time that particle gets there, it will scatter or not scatter or do whatever it does, but with no special dependence on the time at which the process takes place. That's going to be our basic assumption. How do we describe the event of the particle being absorbed at position x equals 0? Well, we describe that by means, this should be psi dagger, shouldn't it? I think this should be psi dagger. It's the daggers that go with the plus signs here, I think in my notation that I used last time. I think that's right.
But then either plus, I say.
I don't think so. I think a plus always went with a minus here. I think so. And then this one would be plus, if I remember. Okay, we describe it in the following by a kind of bookkeeping. It's all bookkeeping, but it's useful bookkeeping. You absorb the particle. This is a field which creates particles. Let's write down the other conjugate field which annihilates particles. It's the complex conjugate, or psi of x and t, which is made up out of annihilation operators, e to the plus I kx, e to the minus I omega of k t. It's just every place, everything is conjugated. E to the minus I kx becomes e to the plus I kx, and so forth. And these are to be thought of as complex conjugates of each other, or Hermitian conjugates of each other. All right, let's imagine, first of all, absorbing the particle at the origin. How do we do that? We absorb it by an operator. Well, we start with the initial state. The initial state has no particles with any particular momentum except one particle with momentum ki. So if we described it in terms of occupation numbers, only the occupation number associated with momentum ki would be non-zero. We can also just label that by saying there's one particle with momentum ki and be done with it. We don't need to specify all the particles that aren't there. But nevertheless, it's useful to keep in mind that when we specify the initial state, we're specifying all of the occupation numbers of all the various quanta, and only one of them, according to assumption here, is present. So there's a 1 here, and all the others are 0, and we just label it by saying, well, there's one particle with momentum ki. Then that particle is annihilated at the origin, if it's at the origin, and let's describe that by psi of x and t, but x is equal to 0. 0 and t. Why is x equals 0? I'm assuming that if the process happens, it happens at the target, and the target is at x equals 0, but it can happen at any time. So that's the process of absorbing the particle at time t. That's what this says. But then the particle is immediately recreated. That's why you say, why does it have to be? It doesn't have to be. That's the model that I'm making. A particle absorbed and immediately re-emitted. That's a mathematical model. It's not necessarily a law of nature about any particular kind of particle. In fact, in the real world, a photon can be absorbed by an atom and emitted later or earlier. So what we're talking about here is a simple mathematical model in which the process happens all at an instant. Particle absorbed and re-emitted. And what's the emission described by? It's described by the creation of a particle also at point 0. So that's psi dagger of 0 and the same time t. But what time? What time should I put there? The same time, but which time? It will matter. So, why 1 or 0? How about let's say it can happen at any time that the particle gets there. Okay, whenever the particle gets there. That's the same as saying integrate this over all possible times. In other words, there is a process in which the particle is absorbed at this time, at this time, at this time, and so forth. So let's not prejudice what time it happens by just averaging or integrating over all possible times. This is a mathematical expression which we can work out. I will show you as we go along what the implications of this integral over time are, but the basic physics of it is that the process could happen at any time. No special time. No particular time is singled out as special. And we get rid of the specialness of the value of time by just integrating over all values of time. Okay. What does this give? This gives the final state. Here's an initial state. These are operators which operate on the initial state and give some final state. How do we calculate the probability that the final state consists of one and only one particle moving with some other momentum. All right, if you remember your rules of quantum mechanics, we take the inner product of this state with the final state. So let's say one particle with momentum k final. This is a number. Remember, a ket vector, operator, bra vector give us some kind of number. Is this number the probability for the scattering? Not quite. We have to square it. We have to take the absolute value of it and square it. Now, I've left out one important ingredient in this expression. We're going to evaluate this. We're going to go through it, and we're going to see what it says. Of course, I'm purposefully, or not purposefully, I would rather be able to explain all of this in complete logical order. But, you know, given an hour to do all of quantum field theory, we have to draw on things that we've done in the past. So in the past, I explained that probabilities are squares of amplitudes, and amplitudes are inner products between initial states and final states. Okay? So here's the thing we want to calculate. But I've left one thing out. I've left out the strength of the scatterer. The strength of the scatterer is a measure of the strength of interaction between the scatterer and the scatteree. So let me give you an example. You could have a charged particle at the origin, which is scattering a photon. A photon comes in, is absorbed by the scatterer, and re-emitted. What is, in that case, what corresponds to the strength of the scatterer? The answer is the electric charge of the charge. The bigger the electric charge, the more probable it is that the photon will get scattered. There is a measure of the strength of the interaction between scatterer and scattered particle, the strength of the coupling between them, which has to be codified somehow, and it is simply by a numerical number put here. It's called the coupling constant, G. G for what? I don't know what G is for. It's a measure of the strength of the coupling or the strength of the interaction between the scatterer or the target and the particle itself. I'll give you an example. Some examples. The scattering of a meson from a proton is a strong process, meaning to say that if the meson is absorbed, if the meson arrives at the location of the proton, it has a high probability of scattering. That's indicated by a large coupling constant. A photon in the vicinity of a charged also could be a proton. A photon is also absorbed and re-emitted by a proton. The probability for that scattering, the probability that the photon gets redirected, is much smaller than the probability for the meson, and that's indicated by the coupling constant being much smaller for the interaction of a charged particle with a... you think of something even smaller? Yeah, a neutrino interacting with a proton has an even smaller constant for scattering off this. That's what made it...
Would that be valid also for an electron?
Well, for the target being an electron or the... Well, right now we're just making a model, in fact, of an electron or something like an electron scattering off a target. So don't think of this as being valid for any real thing. This is a simplified model for a number of different situations. What about the scattering of a graviton by a nucleus? Graviton is the analog for gravity of a photon. Well, it can happen, but it's an extremely small constant. I won't even try to tell you how, 10 to the minus some large number by comparison. All right, so the strength of the interaction and the probability that this actually happens, that the particle gets redirected, is indicated or described by the coefficient g, which appears here. It's just a number, and it's called the coupling constant. It's called a coupling constant. There are many coupling constants. All right, so let's see if we can calculate this. What are we trying to calculate? We're trying to calculate the probability for going from k initial to k final. That's all. Yeah. Question? Yeah.
Now, is there any logic for g being a constant as opposed to being a function of omega or k?
That's a good question. The answer is there is no logic to it. No, there is logic to it, but there are situations where it's a function of omega. All right? I'll show you some situations. As I said, this is a model of a particular kind of simple scattering. There are more complicated kinds of scattering. A more complicated kind would be, and this would really be for the case of a photon and an atom, for example. Photon comes in, atom gets excited, bzzz, and then de-excites by emitting the photon. Okay? Here there's a little gap, a time gap between the time the photon is absorbed and the time it's emitted. This happens to be equivalent to saying that the coupling constant is omega dependent. Okay, so as I said, we're talking about a simple model and just trying to find what the consequences are. There's going to be one important consequence, and it is very general. The rest is not so general. But the one important consequence that I want to get to. So let's just plug away. We're going to just go straight ahead, plugging in for psi its value written in terms of creation and annihilation operators, and then use those creation and annihilation operators to annihilate the initial particle and recreate the final particle and calculate the expression that's up there. The square of it will be the probability. So let's do it. Okay, so yeah.
Question, if G was 1, would that probability must be 1?
If G is equal to 1, yeah, all right. That's a good question. Well, you could ask what happens if G is much bigger than 1. Does that mean that the probability is much bigger than 1? No, it doesn't. It doesn't. It just means that you have to go ahead into a more complicated calculation. This calculation that I'm doing is only correct for very small g. Okay, it's correct for very small g. What you have to do when g is larger is extremely interesting and will be very important to us in what follows. The answer is you have to do higher order perturbation theory. Okay, but we're not doing that now. Well, we're just doing the simplest thing. All right, so let's do the simplest thing and just plug in for psi its value. All right, psi, the first psi, not the psi dagger, but the first psi is a summation over k, not k initial, but just k, a summation index, a minus to absorb the initial particle of k, e to the I kx, e to the minus I omega sub k t, and that acts on the initial state, which happens to have one particle of momentum ki. Yeah.
Since the x is 0,
Thank you. X is 0 at the scatterer. So let's leave it out. E to the I k0 is just 1. Okay. Which terms in this sum will contribute? Only when k is equal to ki will we get anything. Right? Why? Because the annihilation operators give 0 when they act on states where there are no particles. The only particle around has momentum ki, and so only when k is equal to ki do we get anything. But nevertheless, let's leave it in this form just for the moment. Now, what about the other operator, psi dagger? That's also a sum over momentum. I better use a different index because I don't want to use the same summation index twice and get confused. So let's call it L. And now we put a plus of L. That creates the new particle with momentum L times e to the, well, x is still equal to 0. X is still equal to 0, so we don't get anything from here. But then we have e to the I omega sub L times t. What about the final state? The final state is the state with a particle of momentum k final. Okay, which term? All right, first of all, the term in the sum over k which contributes is only when k equals ki, right? What about the sum here over L? What does L have to equal? K final. Remember that when A plus acts to the left, it annihilates. It has to find a particle to annihilate. A plus of L only gives you something when L is equal to K final. So really, both of these sums collapse. Only K equals K initial and L equals K final. That's all there is. What did I leave out? G. Okay. But I've also left out something else. Where is it? Integral dt. It's the integral dt, which is the thing that I'm really interested in. All right, so the only contributor here is k equals ki. What does A minus of ki do when it acts on a state with momentum ki? It just creates a state with no particles, right? It annihilates the particle with momentum ki. What about this sum? This sum is only non-zero when L is equal to K final. So we can put K final here. And when this acts on a state with K final, oh, sorry. Yeah, okay, right. We're okay. This is good. All right. What happens when A acts on the state with K initial? It just gives a state with no particles, right? So that's just no particles. What happens when this acts on a state with particle with momentum K final? It just gives no particles again. What is this number? 1. So that much is 1. So all this operator nonsense of creating and annihilating particles all goes away, and all we have is a number g. That's the probability for the scattering, or that's the amplitude for the scattering, g, nothing else except that we have this integral.
Well, we also have square root of initial and
Not in this expression. I think you're thinking about a relativistic problem.
no, square root of K final.
No. There was only one particle here. Because there was only one particle, yeah, there was only one particle, right? Okay, but the important thing, the real only thing that really I'm illustrating here is the integral over time. And what is it? It's an integral dt, e to the I, omega, let's just call it final, minus omega initial, this is k initial, times t. That's the whole upshot. The time integration gives us an integral over e to the I, omega final minus omega initial t. All of the operator nonsense just gives us a 1, nothing very interesting. The coupling constant gives us a g, and now we have to evaluate this integral. What is this integral? Delta function. This is an example of the delta function. An integral dt of e to the I something times t. Let's see, was it 2 pi times the delta function, if I remember?
Yeah.
I think it was 2 pi g times delta of omega final minus omega initial. Does this ring a bell? Delta of omega final minus omega initial. It's only non-zero when omega final is equal to omega initial. Omega final is the final energy. Omega initial is the initial energy. So somehow, magically, now notice that if we had not integrated over time, we would not have gotten this delta function of energy. So somehow, there's a connection between the fact that, that there's a conservation of energy and the fact that that there's no preference for any specified time. We could have made a model in which the scattering only happens if the time is within some boundaries. Then this integral would have only gone over some limited amount of time. It would not have made a delta function. So the ingredient here, which is closely connected with energy conservation, is time translation symmetry, that every time is like every other time. Yeah?
That whole thing is squared, does that matter?
That's the amplitude.
Oh, the square of the delta function. Well, yeah. The probability, for the probability, we have to square this. This is the probability amplitude. The probability itself will have the square of this, but who cares about the square of a delta function? The delta square of a delta function is also 0 if omega final is not equal to. We have to worry about squares of delta functions, but in any case, this will be 0 unless the initial energy is the same as the final energy. Let's assume the initial energy is the same as the final energy. Then this is the operative important part of the scattering amplitude. Let's call this by its name. It's the scattering amplitude. And the probability for the scattering is proportional to 4 pi squared g squared. All right. The strength of the scatterer, or the probability for it to scatter, contains g squared. They always wind up containing pi's, but the important thing is the g squared. And which final momenta can happen? Well, I didn't specify anything special about the final momentum here. This final momentum could have been anything as long as the energy was the same. So this scatterer has the property that it takes a particle and with a probability proportional to g squared changes its momentum with equal probability to any momentum with the same energy. That's it. So this is a scatterer which can scatter into any direction with equal probability. Okay? Any direction with equal probability. That, of course, is not true of all scatterers. This is this very simple model that scatters with equal probability in all directions, and the coefficient g squared, 4 pi squared g squared in this case, is the probability. So this is, I've shown you many things so far tonight, in particular the definition of a coupling constant, the fact that the integration over time is the thing which ensures energy conservation, which is just another way of saying the problem has time translation symmetry. There was nothing special picked out about one time or another time. And I've illustrated the idea of a scattering amplitude, or the amplitude, the thing which becomes squared in order to calculate a probability. This is a fairly generic set of ideas, but the details can differ. Yeah.
Can you always simplify these things by redefining the position so x is 0?
Say it again, louder.
Can you always simplify this by redefining the position so x is 0?
Yeah. Good question. Yes, in this particular case, yes. The question of what would happen had you not put x equals 0 here, right? That's kind of the question. Okay, what you would have found is there would have been another factor. The other factor in here would have been, in the amplitude, e to the I k initial minus k final times the position of the scatterer. What shall I call the position of the scatterer? Let's just call it x of the scatterer, x of the target. X of the target is a number. X of the target is just the position of the target. When the position of the target was 0, this didn't occur. If the target was moved over to position x target, you would get an extra factor. But what would happen to the probability? No change, because when you square, meaning to say when you multiply by the complex conjugate, this goes away. Multiplying this by its own complex conjugate, which is what I mean by squaring, multiplying by its own complex conjugate, this goes away. So this does not appear in the probability. Get the same probability no matter where the target is, but in an intermediate stage of calculation, in calculating the amplitude, the position of the target would occur. Okay. Yeah.
So it's a very simple model, so you could cram 2 years into an hour.
Yeah.
But the mathematics, unless I see it wrong, seems to say if we said that it didn't matter where it happened, but it happened exactly at time 0, we'd get a different conservation.
Yes. What would you guess conservation would be?
Well, it's momentum and...
Momentum and no energy conservation.
Right.
Right.
And does that have a physical interpretation, or is this more a property of just the mathematics?
Well, of course, in the real world, if we're studying, for example, the interaction of two particles, and we take everything into account, both particles and so forth, the scattering can occur at any time, at any place. Right. But you could certainly imagine an approximate situation where you might, okay, you're asking me, is there ever a situation where here the approximation was we just ignored the recoil of the target, okay? And therefore the momentum was not conserved. Is there ever a situation where energy is not conserved? And that sort of situation is what happens when you have time dependence in the coupling or time dependence in the strength of interaction. Now, yes, there certainly are situations where that can be a good approximation to say something makes a sudden change in the system from the outside, and when a sudden change in the system happens, that's when the scattering takes place. Yes, we can think of situations where that happens. I can. Well, we can try to concoct one. I can't right now. I'm a little too fuzzy. But yes, we can certainly concoct a situation where something sudden happens in such a way that it makes the scattering possible at an instant of time, and then energy would be completely not conserved.
Right. Do most of the coupling constants come from experimental data?
Yes.
And also, you just said introducing a time dependence in the coupling constants, which started making...
Well, that usually means, when there's a time dependence in the coupling constant, that usually means there's something that you've ignored in the system, which is either moving or time dependent, something whose dynamics and degrees of freedom you're sort of ignoring in the same way that you ignored the possible recoil or repositioning of the target here. So I'll try to think of a situation where there's an interesting violation of energy conservation, or where the bookkeeping was such that you threw some of the energy away, but let's come back to it. Yeah, hitting a moving target. Hitting a moving target, right. Hitting a moving target is an example. Where the target, where again, the motion of the target is thought of as completely fixed. Yes.
Right.
And on certain scales, you have to worry about the size of the target versus the
Yes.
the frequency of the size of the wave.
Yeah,
So electron
exactly.
versus X-ray versus gamma
Yeah.
versus.
Yeah. Here, in this model, the size of the target was 0. Yeah, in this, right, and you're absolutely right. Something interesting happens when the target has a certain finite size, and we can discuss that. But let me just come back to the question about the moving target. If you think about it for a minute, of course, if you have a moving target, energy is not conserved. For example, supposing that wall was moving toward me, and I had a tennis ball, and all of a sudden the wall hits the ball and the ball moves off. The energy of the tennis ball, we're not accounting for the energy of the moving wall. We're not trying to worry about that. So if the wall is moving, that corresponds to a time dependence, in this case a time dependence not of the coupling constant, but a time dependence of the location of the scatterer. That would be enough to make energy not conserved, and we could see it in the mathematical formalism. Okay, so to reiterate, these creation and annihilation operators are the tools which allow you to discuss transitions of particles from one state to another state. We have not talked about, well, actually, we did talk about creation and annihilation. Yeah. Let's discuss another situation. Oh, incidentally, supposing psi was the field operator for an electron. Each kind of particle has its own separate field. Okay? So electrons have a different field than photons. When you put psi here, you better specify what particle you're talking about. Okay? Let's think of the electron. Psi describes electrons now. Here was a process in which an electron came in and an electron went out. What happened to the total charge? Did the total charge change? No. One particle came in, one particle came out. Now, let's imagine a different situation. Let's imagine a situation where one electron comes in and two electrons go out. Okay, crazy. I mean, it can't happen, but let's for the moment nevertheless try to imagine it. How might we describe it by the same kind of mathematics? One electron comes in, two electrons go out. How do I modify this? And here my simple model is two electrons go out from exactly the same point. Yeah. We might put another, we might square this. In other words, psi of 0t, psi dagger of 0t, psi dagger of 0t, psi of 0t. Oops, there should be a t here, right? Yeah. Okay. What about, now this of course can't happen in nature because electric charge is conserved. This corresponds to the annihilation of one electron and the creation of two. Bad idea, but nevertheless, let's write it down. What about two electrons in and two electrons out? Is that okay? Well, at least it doesn't violate electric charge conservation. How would we describe that? Another psi. Psi, psi, psi dagger, psi dagger. How about two electrons in, three electrons out? Psi, psi, psi dagger, psi dagger, psi dagger. Okay, which ones of these are allowed? And what's the rule? I'm not deriving a rule now. We're just going to observe a rule.
Same number of creation and annihilation.
Right? Same number of psis as psi daggers. This is not allowed. This is allowed. This is not allowed. The rule is same number of psis as psi daggers. Is there another way to express that?
Does the order matter?
What's that?
Does the order matter? Does the order of the operator?
It's not a question of the order of the operators. It's the number of psis versus the number of psi daggers. Right? When the number of psis, all right, when the number of psis is different than the number of psi daggers versus when the number of psis is the same as the number of psi daggers. How can you diagnose these combinations? Of course, it's very easy just to count the number of psis and psi daggers, of course. But let me give you a mathematical diagnostic that really does have a deep meaning. Let's imagine a transformation. Now, psi dagger does mean the complex conjugate of psi. It is the Hermitian conjugate in the language of quantum mechanics, but the Hermitian conjugate is the analog of complex conjugate. Let me imagine that I take an expression like this, just a mathematical expression like this, and I transform psi by multiplying it by a phase. A phase means an e to the I times some number, let's call it alpha, times psi. I'm just doing now blindly playing a game. Wherever I see psi, I multiply it by e to the I alpha times psi. What happens to psi dagger? If I multiply a complex quantity by e to the I alpha, what happens to its complex conjugate? E to the minus I alpha psi dagger. What happens to objects that have an equal number of psi and psi dagger? They stay the same. What happens to objects which don't have an equal number of psi and psi dagger? They change. So we could characterize the allowed processes by the ones which are described by operators which are invariant, unchanged, by the operation of changing the phase of the operator. Now that, Indeed. But for the moment, let's give it a simpler name. Invariance under redefining the field so that you change its phase. And overall, you change the phase by a constant phase factor if the description, if the interaction expression here is invariant, then charge is conserved. If it is non-invariant, then charge is not conserved. What happens, supposing I had psi plus psi dagger, what kind of thing does that correspond to, incidentally? All right, I'll leave that to you to think about. But is this unchanged by phase? No.
Yeah.
No.
Isn't that the real part?
This is the real part of psi, and if you multiply by a phase, you change the real part of psi. So that's not a quantity which is invariant.
Question. If you have a target and you have an electron impinging on a target,
Yeah.
you may have many secondary electron emitted.
Yes. Well, wait. If you have, what kind of target? A target full of electrons?
Yeah.
Well, sure, you can have, yes. Yeah, right. You say, what happens if you have an atom and you hit the atom with an electron and 75 electrons go off? Well, charge is not violated, of course. What has happened is the atom has changed. All right. This is a situation in which you cannot get away with ignoring the dynamics of the target. In the particular, the important dynamics of the target is the change of charge of the target. You can't, in this case, treat the target as though it was a completely passive thing. You've got to remember. Right. What's that?
The target changed.
Yes, that means the target itself has to be described by a quantum field. All right? And we can discuss that. I think we've gone far enough for tonight. All right? So what have we found? We found that time translation invariance corresponds to energy conservation. Phase invariance, we can call this phase invariance, corresponds to charge conservation. And we haven't worked it out yet. We will work it out next time, that spatial translation invariance corresponds to momentum conservation. I'll show you how that works next time. But we're making our way slowly into how particle physics processes are described by fields. That's our goal for the next, one more lecture on it. I don't know, maybe half a lecture on it. And then we'll move into some of the symmetries and some of the more interesting laws of particle physics. Yeah.
Just to, I don't know, work it out in the math, but we could have just as easily have had a process that was psi, psi dagger, psi, psi dagger, psi, psi dagger, right?
Yes, yes, but it's not hard to yeah, okay, right, that's great. I've chosen always to put all the daggers to the left and the psis to the right. Remind me next time and I'll show you how to rearrange other expressions so that they become like this. I know what you're asking. You're asking what would happen if instead of this we put psi, psi dagger, psi, psi dagger. And I will tell you next time. But they still match. This is allowed. No, not quite. Not quite. Not quite. Not quite. Remind me next time. I'm too tired now to start going into it. But remind me absolutely next time, what is the difference between this and this? And I'll show you next time. All right, I actually left time for some questions. If you want to ask some questions, I just have run out of steam well, it's not that yeah, go ahead.
Have you noticed that invariance implies charge invariance?
Well, it's sort of trivial. If you have as many psis as psi daggers, that means the interaction eats the same number of electrons as it spits out. All right, each psi annihilates an electron, each psi dagger creates an electron.
No, have you proved that phase invariance implies charge conservation or the other way around? Or?
All I did was point out that all of the objects with equal numbers of psis and psi daggers will be invariant under the phase operation here. If they have different numbers of psis and psi daggers, let's take a case. Psi, psi dagger, psi dagger. You get it, right? I'm not sure what the rest of the question is. If they have equal numbers of psis and psi daggers, it's phase invariant and it conserves charge. If it has different numbers of psis and psi daggers, it's not phase invariant and it doesn't conserve charge. So we're just observing that when it's phase invariant, it conserves charge. When it's not phase invariant, it doesn't.
There are two other rules you stated at the same. You stated two other rules at the same time. Conservation rules.
Energy, momentum, and charge for the moment. We haven't gone through momentum conservation, although it was mentioned by somebody here. Asked me if the process can happen at any place instead of any time, then yes, then it conserves momentum. But we'll come to it. We'll do that case.
That's Emmy Noether's.
Yeah. In classical mechanics, it's Noether's theorem. In quantum mechanics, it's even simpler, but here I'm sort of short-circuiting all of that discussion by just showing you how it works mechanically in terms of these quantum fields.
Question. Up there, the probability of that first system is 4 pi squared g squared. Does that mean when you empirically assign a value to the coupling constant that it must be less than 1 over 2 pi in that particular case?
It must be less than 1 over something, or your model is very incomplete. If you ask me in what way it's incomplete, I will tell you. In what way it's incomplete is that the real scattering process is not described by just a particle coming in and getting scattered out. It's described by something more complicated, which is a sum of amplitudes in which the particle comes in, scatters off the target, comes in, goes back out, comes back in, scatters off the target twice, comes back in, scatters off the target 3 times. It's a whole infinite series. Each term has a factor of g in front of it. It's only when g is small that only the first term is important. But we'll come to that. This is a basic theme that when the coupling constant is small, you can get away with the simplest minimal process. When the coupling constant gets large, one has to, well, let's just call it what it is. One has to sum up an infinite number of Feynman graphs. Basically, these pictures that I've drawn are Feynman graphs. And the vertices of the Feynman graphs are described by these operators. Okay, the vertices of the Feynman diagrams tell you the basic elements that can happen. Particle comes in, bounces back out. That's psi times psi dagger. Two particles come in and bounce back out. That's psi dagger, psi, psi, or whatever. And we'll give things their proper name next time. Yeah.
Are there any situations when coupling constant has imaginary component?
Well, yes.
What are they?
You want me to the existence of a theta parameter in QCD. The existence of a theta parameter in QCD. I'm sure that means nothing to you. Yeah, it does happen that there are complex values of coupling constants. It usually means that time reversal invariance has been broken. Complex coupling constants are usually an indication of a violation of time reversal invariance. That's really what it comes down to. Now, you can't see that from what I've told you up till now. At least if you can, you're smarter than I am. I can see it, but only because I know how to see it. But it's not obvious. But that is the case. Complex coupling constants mean that time reversal invariance is broken. In other words, things don't look, if you run the process backward as a movie going backward, it's not a possible process.
Yes.
You said at one point also that instead of having the scattering occur, the outgoing particle at the same time as the incoming particle could be before or after. You also mentioned before. Does that happen?
Not now, but yeah, no, I did say that, and I sort of regretted it the minute I said it. But we will. No, it's a fair question, but it's not the time for it now. Yeah.
Jane Franklin used to say it laughs before you tickle it.
What's that?
Jane Franklin would say it laughs before you tickle it.
Okay. Yeah.
You're probably going to say you'll get to this at some point, but how do you turn this into something that's relativistic?
Again, you're jumping way ahead. I'm trying to go slowly, and everybody's pushing me to get ahead. Okay, you really want to know? You add this and this and put a square root of omega k in the denominator. No, we're jumping ahead. I mean, yeah.
And you talked about charge conjugation. Conservation with that phase factor. But the rest mass, m, that doesn't change also during the phase.
In a non-relativistic process, but in a relativistic process it can. And there's nothing in basic quantum mechanics which says that rest mass can't change. It's a combination of quantum mechanics, or not even quantum mechanics, even just classical mechanics, together with an invariance principle, and the invariance principle is Galilean invariance, which is an analog of a non-relativistic analog of Lorentz invariance. But yeah, it is true in non-relativistic situation, total mass can't change, but it can in relativistic scattering. So what did you want to ask me exactly?
Well, it's just that logically we think of rest mass conservation in the same terms as charge conservation.
No, not at all. Not at all. One is absolutely true in nature, the other is only true for very, very slow velocities, right? There's nothing sacred in physics about conservation of rest mass, and what's more, it's not true. An electron and a positron annihilate into 2 photons. There's no conservation of mass. There is a conservation of electric charge. So one of them is a sort of accidental, non-relativistic fact. The other is a deep underlying symmetry of nature, which happens in simple case just to correspond to this phase invariance. Next time we'll talk about fermions. We'll talk about what happens if you have more than one species of particle. Supposing you have electrons and muons and quarks and so forth. How do you describe all of this? What's allowed, what's not allowed, what kind of processes, and all in the language of quantum fields. Yeah.
Strictly speaking, with your scatterer example you gave us, you said it was an electron, but I thought we only knew about bosons so far.
Ah, good point. Good point. Good point. Good point. Yes, 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 yes. Good point. Yeah. So we have we're talking about a bosonic version of an electron. Yeah. Sorry, I completely missed that. You're right. Right. But there are particles in nature which carry electric charge. Yeah. Right. Exactly. A charged pi meson, a slowly moving charged pi meson, would be an example of a boson which you would describe in this way. Yeah. Yeah, so good. Absolutely right. Thank you.
For more, please visit us at stanford.edu.